Let's take a few minutes to get practice with one-step synthesis problems. We're asked to provide a synthesis for these three molecules. Let's look at this thioether first. Now we have to look for a functional group or somewhere else that we know we've learned how to make a bond. And really the CS bond on either side of the S is going to be a good starting point. So we could make a molecule that involves, or we could make a synthesis that involves creating that bond. So let's think about that first. I'll draw a retrosynthetic arrow. Remember that the retrosynthetic arrow means that this molecule was made from whatever I draw over here. It's easy to get confused when we first are confronted with these large arrows. So remember that we're working backwards now. All right, so if I want to make this CS bond, I need the sulfur to be a nucleophile probably, and the carbon to have a leaving group on it. So let me draw, there's a 4-carbon chain. I'm going to put a leaving group on that. And then I need the sulfur with whatever's on the right side of the sulfur. It's just a 2-carbon chain, so I'll redraw that over here. Give it an anion, and I can have a good nucleophile, good electrophile. I can get an SN2 reaction to happen. We could also create this bond. Another retrosynthetic arrow. I could start with the sulfur attached to the 4-carbon chain. Again, I'll make sure it's a negative charge. And then I could put a 2-carbon electrophile in here. Let's use a bromine as the leaving group. And there's my 2-carbon chain. And both of these would react to form this product as well. Also an SN2 reaction. When we're faced with two options here, it's a good idea to ask ourselves if one of them is better than the other. Both of our alkyl halides are primary. Both of our sulfur nucleophiles are S-. There's really not a lot of difference between these two, and I would say either of these would be perfectly acceptable to make our target molecule. Let's look at this alkene. What if the goal was to make that alkene? We've learned how to make alkenes via E2 or E1 reactions. My suggestion is to stick with E2 if at all possible. And so we can perform an elimination if we have a leaving group on one position of that alkene. So let's look at this possibility. There's my leaving group, there's my hydrogen, and I will use methoxide as my base to remove that hydrogen, creating the more substituted alkene. Another option, let's go with green again, would be to put the leaving group on the other side of the alkene. And in this case, I'd again probably want to use methoxide. I would hopefully remove that H and create the alkene. So the question is one of these a better choice than the other? There's another beta position right here, and I might end up with that if I were to remove the red hydrogen. If I were to look at another beta position here, that I think would give me the same exact product as my initial, if I call this HA and HB. I believe HA and HB, both being lost via E2 reaction, would give me the same identical product, and that's what I want to think about here. So that's fine. There is HC, however, that would give me a much less substituted alkene, much less stable, so likely that's not going to be a competing reaction. I think HA or HB would be more likely to be removed. Both of those would give me the desired product. Whereas the red hydrogen here probably is going to be a bit more competing. So I think I'd prefer the purple pathway in this case, but there's really not a heck of a lot of difference. Let's look at the third option. Again, we're making an alkene. We can do that by putting or starting with a leaving group on one of the positions of the alkene. We might consider this as a E2 proposal. However, look at this as a primary substrate. strong base, strong nucleophile, more likely we're going to get SN2 chemistry to happen as opposed to elimination. So in order to prevent SN2 from happening, we could bulk up the base. Could use a much bulkier base. That would remove the only beta hydrogen that's present. That's the only option, and that would give us the desired product. So this would work. Perhaps the larger base would make it a slower reaction, but by and large I think this is a fine choice. Let's look at another option. We could use this starting material. And of course there are 3 beta positions here. And if I reacted this with a large base, I could try to favor HC as being removed as opposed to HA or HB. So that might work too. However, there would be some competing side reactions. So this would be a minor product, whereas I don't think we'd have any minor products with the purple option because we couldn't have any SN2, and we've got the large bulky base to prevent the SN2. We've got only one beta hydrogen. There's only one beta hydrogen to choose from. Can only give us one outcome. So I think I would prefer the purple option in this case. Okay, let's look at some other alkenes. In this case, the top one, we are directed to make just that stereoisomer, not the other stereoisomer. So let's just go ahead and label these. This would be the E stereoisomer. This would be the Z. We want to make just that stereoisomer. And we can do that by judiciously putting in the leaving group and the beta hydrogen. So one option would be to have our leaving group right there. However, this leads us to 3 different beta positions. I propose HA and HB are identical positions, and I'm trying to draw HC right here. HC is different. So either HA or HB could get us to the desired product. However, there are 2 HBs. One of those will give us the E stereoisomer, the other will give us the Z stereoisomer. So this one is not stereo-specific. It is going to be stereo-selective, but not stereo-specific. So I don't think this will work. We need to put our bromine in a different location. So let's use the other side of the alkene. That is the stereo center. Now there is a beta hydrogen right here, and there's a beta hydrogen right there. If we choose a small base, we can favor HB loss instead of HA, so that might help us get to this desired product. And if we set up this stereo center properly, we can favor just this stereoisomer because this, you'll notice, HB is on a stereo center. So in order to get the hydrogens, or I'm sorry, the methyls on the same side, I think I want to leave my bromine on the wedge and put HB on the dash. So I'm going to erase these things here and redraw them. So I believe that if you drew a Newman projection here, you could recognize that HB and the bromine are 180 degrees from each other. And you'll also recognize that the 2 methyls are on the same side, which is what we want in our desired product here. So I think this is the right stereoisomer to start with. It will provide us with a stereo-specific product. And if I react it with a very small base, let's go with methoxide, I could favor HB loss over HA and thus get as much of the desired product as possible. So you see here I had to analyze both the regiochemistry and I had to figure out what the stereochemistry should be in my starting material to get me to the desired stereochemistry in the product. One last question here, a little more simpler than elimination. This is simply creating this alkyl iodide, and this is a stereocenter, so we can probably make this via maybe a tosylate and sodium iodide. That would work. You can really put any leaving group you want here, and any source of iodide. Sodium iodide is the easiest. It might be better if this one said only enantiomer. That would make it a little more clear that we'd want to effect an SN2 reaction in order to make this, this stereoisomer. And so this would be SN2. You can just label that. Don't really have to, but it's good practice. If you wanted to label the top one, this would be produced via E2. So the lesson here is if we can stick with E2 and SN2, we're going to get much fewer numbers of products. So that should be one of your goals, is to try to make things via SN2 and E2.